So in this video, we're going to talk a little bit more about some complex hypothesis testing, and we're going to revisit our height versus ideal weight versus gender form to give us some examples of this, and we'll also talk a little bit about some of the other techniques. And a lot of the techniques described in this particular section are known as analysis of variance. And you will see analysis of variance used frequently in experimental research. So what we're hoping to accomplish in this particular video is first just introduce the notion of analysis of variance. What we will then do is we will discuss the notion of covariance. These are things that you want to separate out of your experiment when looking at effects on dependent variables. Then we'll take a look at gender specifically as a covariate in height versus ideal weight. And then we'll talk about the challenge of multiple dependent variables. And the technique that can be used there is sometimes referred to as Manova, whereas analysis of variance is known as ANOVA. And then finally, we'll just talk a little bit more about modeling versus hypothesis testing. And then the last two videos in the sequence will focus almost entirely on building models, which for the most part is likely to be more useful for practitioner researchers as opposed to academic researchers who tend to be more focused on hypothesis testing. So let's start by considering two hypotheses. One hypothesis is that men have a different ideal weight than women, and then the other hypothesis would be ideal weight differs with height. Now, both of these are framed in a way where there is a null hypothesis, which is to say men have the same ideal weight as women, and ideal weight is the same or is independent of height. And then both of them have a testable assertion that there's actually a difference. And in our ideal height versus weight survey, we actually can test both of these hypotheses using a technique known as analysis of variance. Now, mind you, we also saw that we could use the correlation to show relationships, but in the case of analysis and variance, we're specifically testing these hypotheses. So in order to test the gender hypothesis, let's go over conceptually what we want to do. So we've got a sample that has both men and women responding with respect to the question of what is your ideal weight. So what we really need to do is we need to think about two different blocks, the male observations and the female observations, and we want to make a determination, are their true means the same? So our null hypothesis is that the true mean for men and the true mean for women are exactly the same. So how do we conceptually go about doing that? Well, the first thing we do is we compute the means for our male observations and for our female observations. Then we determine the variance of each set of observations. And then we determine the likelihood that these two different means could arise randomly given the variances that we computed. And this whole process is called analysis of variance, and naturally we're going to get the software to do it as opposed to actually doing these computations. Though if you went back 100 years, this was exactly what they had to do. They had to actually do all these computations by hand. So once again, we can use the JASP tool to do an analysis of variance. So I'm going to bring up JASP. I am going to open our cleaned height and weight file. And then I am going into analysis of variance. My dependent variable, that is the variable I'm trying to predict, is ideal weight. Gender is the fixed factor. This is what is going to break up my sample into boxes. And if we take a look here, I'm going to have to expand this a little bit. I'll come over here. And what we see, once again, is we look for that p-value less than 0.001. And what it's telling me is that gender does, in fact, predict a difference in ideal weight, or a difference in ideal weight is associated when you separate it up into male and female blocks. So that's a very, very simple analysis of variance with a value that can only have two values, male and female, which, by the way, is pretty similar to what we did in the t-test. So it shouldn't be surprising that our analysis and variance and t-test come up with the same information. Testing the height hypothesis is a little bit more complicated. And the reason for this is that whereas we had two genders, male and female, which allowed us to break it up into two nice pieces, in heights we actually have quite a few more heights because we're measuring heights in inches. And so we might have 10 different blocks. But conceptually, it's the same process. What we're looking for is to test the hypothesis that the mean in all of our blocks is the same. That's the null hypothesis. And we want to reject it through our analysis. So the process that we follow is that we compute the means for different sets of observations and realize some of these blocks may have very few observations or no observations whatsoever. We determine the variance for each set of observations, and it'll make assumptions about the variance being the same across the board if it has to, because that's the only way it can do the computation. It will determine the likelihood that the difference could arise randomly, and if any of the means appear different, we're going to reject the null hypothesis. So to run this analysis, once again, we'll move away from the slide deck and bring up our actual data. And what we'll do is we'll get rid of gender as a fixed factor from our last analysis, and instead we'll put in height in inches. And what we see here is that we also can reject the null hypothesis here. I guess you can't see that. I'll bring it over. Which is to say that the p-value is again less than 0.05. So it appears that the height in inches does impact the ideal weight. Now, there is a statistic here called the F statistic, and the F statistic is a source of overall fit. And the F statistic is much higher for the gender test than it is for the height test. And one of the reasons for this is that in the height test, we've got it broken up into a whole bunch of little boxes, making it much, much harder to be confident about our estimates of variance, whereas in gender we only had two boxes, male and female, in which to group our observations. So even though we see that there's a difference in means, this suggests an overall lower level of confidence. Now, it turns out JASP doesn't go any lower than 0.001. Otherwise, we'd actually see this in terms of different p-values. So in the workshop, what I did was have everybody read an excerpt from Paradigm Lost, which is a paper that was submitted to Informing Science that talked a little bit about some sort of statistical issues that frequently came up. And in this particular reading, what happened is they were trying to estimate the weight of trains based upon the number of cars. And what they got was a much lousier regression than they thought. You know, they basically had the number of cars and the weight, and it wasn't a really good fit at all. And so they studied it, and what they discovered was that there were two types of cars. There were double cars, and then there were single cars. And the old timers had seen the evolution of double cars, so whenever they made the estimate, or whenever they counted cars, whenever they saw a double car, they would count it as two cars. Newer people coming in thought a car was a car, and so when they saw a double car, what happened was they would count it as a single car, and if they saw a single car, they count it as a single car. And so when they corrected for new people and for old timers, what they discovered was essentially there were two different curves. Well, if you're trying to find the relationship between weight and the number of cars, there may be time, in this particular case, you're not really that interested in the difference between the two people measuring it. You're actually trying to predict the weight. But you would need to correct for the fact that different people were measuring the trains in different ways. And so that's sort of the upshot of that case. So we discussed that. And now we consider the implications for height versus weight. Because one of the things that we might want to ask is the question, do men actually feel that they've got a higher ideal weight than women? But to make that a useful question, what we need to do is we need to adjust for height, because we know that taller people tend to have a higher ideal weight than shorter people. And if women are on average a little shorter than men, then it would not be surprising at all if they had a lower ideal weight. But what we're really interested in doing is testing the difference in gender based controlling for the height. And so height in that case becomes a covariate. And what we want the program to do is to adjust for height as much as possible, and then after the adjustment for height, it will then look at the difference between the two genders, and that will basically separate out the height effect from the gender effect. Now, the process used to do that is known as ANCOVA. ANCOVA is just analysis of variance with a covariate in the middle, so that's the co. So it's ANCOVA versus ANOVA, and the package that we have, JSP, allows us to do that. So before we actually run the test, just to summarize, ANOVA is a test to see if means are equal, and we reject the hypothesis that means are equal if the p-value is less than 0.05 or whatever we choose that to be. There's no real magic in 0.05. It's just been adopted as a significant value sort of by tradition. But if you care very much about the results, you might talk about p being 0.01 to be sure that you're not making an error. But anytime you lower the p-value threshold, which is known as the alpha value, you increase the risk of missing an effect that's actually there. Anytime you raise the p-value, like to 0.1, you're raising the likelihood that you will claim there's an effect which isn't really there. So this is the difference between type 1 and type 2 errors. And for the most part, researchers are more worried about type 1 errors, which is which is claiming an effect which isn't there, as opposed to type 2 errors, which is missing an effect that is there. So at any rate, the ANOVA computation can be adjusted to mathematically try to remove as much as possible of the effect of other factors, which are the covariates. And the benefits are that it allows us to do this hypothesis testing without creating more and more boxes, because if we make each covariate a separate box, now all of a sudden we've got lots and lots of boxes to fill, and we need a certain amount of data to do the analysis of variance. It also prevents us from ignoring factors that we know are important. I mean, nobody really doubts that your actual height is going to impact your ideal weight. It does require more assumptions than ANOVA, and like ANOVA, it only tells you that the means are equal. It doesn't really tell you anything about the strength of the relationship. So with that, we'll actually take a look at doing an ANCOVA on gender adjusting for height. So, since we've already got the information in JASP, what I'm just going to do is I'm going to open up JASP, and I'm going to go to ANOVA, and I'm going to go to ANCOVA, and the difference between ANCOVA and ANOVA is that we now have these covariates. So what we're going to do is our dependent variable is still the weight. We're trying to predict the weight. What we're interested in is, does gender have an effect? So gender will be what we use to break it up into boxes. And then the covariate that we're going to adjust for is height in inches. And so here, I'll just move this over so we can see what the results are. And here what we see is that gender has an effect, a significant 0.001. Now, it's not a gigantic effect. It's not less than 0.001, but 0.001 is pretty good. Height in inches, the covariate, clearly has a relationship. So as part of the process, it's computed whether this is a significant factor or not, and it appears to be a very significant factor in predicting it, more significant than gender. But what it does suggest is that at a given height, the women in our sample were likely to predict a slightly lower ideal weight than the men in our sample. Well, actually, I take that wrong. I take that back. They predicted a different weight because the analysis of variance is simply a test that the means are equal. It could be higher, it could be lower, and that's one of the problems with these hypothesis tests. They tend to give you true or false answers when you want more information, and that's where modeling comes in, something that we'll talk about in much more detail in the next lecture. So, analysis of variance, ANOVA, tests a single dependent variable. But sometimes we actually want to test a whole bunch of different dependent variables to see if they're affected by different factors. And that process is called Manova. For example, in our food survey, we had two dependent variables. We had the taste and we had the nutrition. And so if we were trying to determine if all of those dishes had the same mean value, we might be interested in, do they all have the same mean value for both nutrition and taste? Because if they do, then it doesn't really matter which of them we choose. If they have any differences, then we might care. So it's really a test to see if all the means are equal. And what I'll show on the next slide is a Manova that I did in one of my research things, which is where I was dealing with a bunch of possible educational outcomes from a course, and I was trying to determine if they were affected by things like gender, experience, ethnicity, and so forth. And since I was interested in if any of the variables were affected, Manova was a test which basically allowed me to look and see if these other variables had any effects at all. In addition to Manova, which tests multiple independent variables, multiple dependent variables, you can have ANCOVA, which tests multiple dependent variables with covariance included as well. And right now, JASP does not do Manova or ANCOVA, but that is slated to be something that is added to the package in the fairly near future. They have that listed as something that's coming up. So it may well be that JASP will start to do those tests by the time you're actually looking at these slides. So here is an example of a table from a paper that I wrote where I was looking at a self-paced delivery of a programming course that I had developed, and this was written in conjunction with a doctoral student. And the idea was basically to determine if this course had good properties in terms of the nature of the students coming in. Because in the world of computer programming, there's been a real problem. There seems to, right now, the number of women going into computer science has dropped dramatically. In the early 1980s, it was like 40% women, and now the number of women going into computer science or engineering has dropped, down to like 10%. So there's a concern that the way we're teaching computer science does not affect women properly. The same problem occurs with minorities. Another problem that we have is that people who come in with experience tend to have a big advantage in an introductory course over people who come in without experience. And so what we're really interested in finding is a course that does not show huge differences in outcomes based upon the nature of the people coming in. And examples of these potential variables might be gender, ethnicity, student status, are they full-time or part-time, employment status, have they taken prior programming courses, have they taken prior courses in the C programming language, which was what the course was on. So those are all the things that we're interested in seeing. Are the means for all these the same? The thing is, we also had a lot of different ways of assessing whether the course was successful for the student or not. There's the letter grade. There were the university course evaluation items. Did the student like the course? There was satisfaction with assignments. There was satisfaction with other aspects of the course, for example, the way it was organized. Did they believe they learned something, and did it affect their view of the attractiveness of programming careers? And I had a giant survey that I had literally, I think, 500 students complete over time, where we were actually looking at this. And so what we were interested in doing was basically seeing if these characteristics affected any of these values. And the interesting thing we discovered is that we saw virtually no effect across all these dependent variables. We found a few 0.05 effects, but we did, dozens and dozens of tests, and no more than 5% of our tests came out 0.05, which is what you'd expect. So what this said is this particular self-paced design did not suffer from being very sensitive to gender, ethnicity, student status, and so forth. And so that was considered a very positive finding. In this particular case, we did not want to reject the null hypothesis that all the means were the same. We were actually hoping that the means would be the same, because that would provide support that we're not having a major effect as a consequence of the student characteristics coming into the course. So as we come to the end of this particular segment of the workshop, what I wanted to emphasize is, once again, this difference between model building and hypothesis testing. And when we're talking about hypothesis testing, what we're talking about is framing questions in true-false terms. We test hypotheses in order to develop theory, which is something that is highly prized by academics. And it doesn't really worry if what we're testing is being useful. And this is actually one of the complaints made about hypothesis testing, because a lot of times, if you gather enough data, the test becomes so sensitive then you can pick up differences, such as the difference between the weights of the head and tails of a coin, that are not of practical significance. So that even if a hypothesis test is successful, we were able to reject the null hypothesis, that doesn't mean the effect is important enough so that it justifies the cost of whatever it takes to implement what you're testing. Now, model building is a little different. Model building basically creates a structure that you can use to make predictions or better understanding of processes possible. It allows us to assess the positive and negative and magnitude of the different contributions of various factors, whereas in the analysis of variance, we're simply saying, okay, they have an effect, whereas in our models, we can make an estimate of how large the effect is. But, of course, it's subject to the fact that if our underlying model is invalid, we can often have erroneous or spurious confusions as a result, and this has been one of the areas of my research. But If you're a practitioner, you're going to be likely to be much more interested in models as opposed to a pure hypothesis testing, because the pure hypothesis testing can be very good in writing for top-tier journals, but it may not be what you need in order to actually make useful decisions. So when we ran the workshop, this was the end of the first day, and the first day was really focused on hypothesis testing. Now, for the remainder of these videos, we're going to be focusing on the second day of the workshop, which was focused much more on model building and sort of validating research. And so we will talk about fitting a curve to data, which is a lot more interesting in many cases than simply telling us whether data is, whether means are equal. We'll talk about multiple regression, which allows us to take account of multiple factors at once. And actually, techniques like ANCOVA actually use the same underlying analysis as multiple regression. They just present the results in different ways. So multiple regression is a very powerful technique. And when I did my MBA at Harvard and when I did my doctorate, multiple regression was covered in great detail. And many of these other techniques were simply mentioned in the doctoral program, and they weren't even mentioned in the MBA program. So we'll spend some time on multiple regression. Then we'll talk about some variations on regression under different circumstances. For example, if your dependent variable is like a yes or no variable, you probably would not normally want to use a normal multiple regression for that. Then we'll talk about some of the challenges of working with many variables and how we might try to abstract sort of general principles from large collections of variables. And this is relatively advanced stuff, but it's stuff that you might encounter in some of the research that you read, especially if you're dealing in areas like analytics or marketing. And we'll talk a little bit about research rigor and what we mean by rigor and how we assess rigor. And then finally, we'll talk about some exploratory techniques that you might use when you really don't know what's going on, and so you've decided you want to try to, explore building your own theories.